Hello, everyone. Thank you very much for coming to my talk on why writing a pinch-to-zoom component is a lot harder than you think it is. So let me first give a quick introduction of myself. I am Ollie, and I work on the AG charts team, which is basically just a front-end library for rendering data visualization charts, such as pie charts, bar charts, line charts, those sort of things. And we've got lots of different features. One of the key features is that our charts are interactive. So you can obviously click it with the mouse. You can also use it with a keyboard if you have accessibility needs. And obviously, you can also use it with touch input if you happen to be on a mobile device. And so a couple of months ago, I had a feature request coming in that we wanted to add support for not just one finger, but two fingers. And broadly speaking, this is the problem that we wanted to solve. We wanted some sort of, zooming and panning features. And so I'm sure you're all kind of familiar with this. You've probably used something similar like Google Maps. But essentially, we wanted a panning feature where the user could put two fingers, move those around, and adjust the pan of the viewport. And something similar with zooming, where the user could put down two fingers, spread them apart, bring them close together to adjust the scaling. So when this feature request came into me, obviously, me being the good programmer that I am and all, I did what any good programmer would do, and I said to ChatGPT, how do I do this thing? And ChatGPT has said, oh, you do the thing like this, okay? So this is what I like to call the classical solution. So basically, the way that it works is when you've got two fingers, they both got X and Y coordinates, and you use those two touches to calculate two different variables. One variable will be sort of like the center, or you can think of it like the average X and Y positioning. You track that average, and as that changes, you can adjust the pan with that. Then the second thing you calculate is the distance between those two touches. You can calculate that using the Pythagoras theorem, and as that changes, you can adjust the zoom. And so that actually works for most use cases. So here, as you can see an example on the left-hand side, that's a zoom pan feature that I'm sure you're all very familiar with. As the user pans up and down or left and right, it changes the zoom. But critically, it keeps the X and Y axis scaling values in proportion with one another, which is good. That's actually what you want, because you don't want to distort the image. You still want it to kind of look like Manhattan Island. You don't want it to look like some other weird shape. But here's the thing. I thought, with a chart, wouldn't it be nice if we could distort the image? Because the user, as you can see, may want to adjust the x-axis or just the y-axis, or they may want to have some more fine-tuned control as to what data they view. So obviously, the classical solution is not going to work for us because we want independent x and y-axis. So then, me, good programmer, I go back to ChatGPT and I'm like, oh, no, I want the x and y-axis to be independent. And then ChatGPT obviously is like, oh, that's a great idea. That can really improve the user experience if the x and y-axis is a very enthusiastic guy. Then he gave me a solution, and it didn't work. And I was like, ChatGPT, I need a solution that works. It's like, oh, yes, I understand. It's very frustrating when the solution doesn't work. Here's a solution. Another solution doesn't work. I did that like 5, 6 times, and eventually I was like, OK, shut up. Let me solve the problem myself. So I kind of thought, OK, so let's try to forget about the code for the time being and try to think from the user's perspective. How do we design a good user experience with touch? So I did some research, and I came across this really useful guideline written by Android. It's very good. I recommend that you read it if you're interested. But essentially, it explains that you have to have something called a realistic touch UX. And so as you can see, the good example there on the left-hand side, as the touches move, the UI components move in, perfectly well in sync with that. Whereas the bad example, you can see like the UI components are like lagging behind, or they're moving too quickly or too fast, and so that's bad, we don't want that. So how do we do that on the chart? Okay, let's look at a use case. So for the panning, let's say, for example, the user puts down two fingers on these two markers, on the star and on the plus sign, and then they move those two fingers to the right-hand side. Well, we want realistic UX design, so they should still be touching the same points. What about for zoom? OK, let's look at a similar case. The user is pressing down the plus sign and the multiplication sign, and then they move those two fingers closer to one another. Oh, well, that's interesting. we want exactly the same thing. The user is still touching those two same markers. So yeah, that is very interesting, because initially we thought that the zoom and the pan, they were two different features, but as it turns out, they're both the same thing. What we want here is that we want a feature that when the user touches stuff and moves those touches around, we want the touches to still be touching the same stuff. And now I've said a lot of stuff, but you're probably thinking, what is he talking about? What are we actually trying to solve here? So let's narrow it down. Let's just think about one dimension for the time being. Just focus on the x-axis. So here we've got this HTML number line, a one-dimensional component with 2 moments in time, start and touch move. Let's hone in on what we're supposed to do when we receive a touch start event. So what are our inputs at this moment in time? Well, obviously, we know the screen offset and the width of our number line. We'll call that Rx and Rw. That's in pixels. OK, what else do we know? Well, we also know the offsets of the touches, because we received that from the touch start event. We'll call that A1 and A2. That's also in pixels. And obviously, we know the zoom constraints of our component, because we've initialized that from the get-go. They'll probably be like 0 and 1 or something. Yeah, but yeah, we know what are the zoom constraints, Z-min and Z-max. And so what we're basically looking for at this point in time is we need to find some way to remember that the user is touching the numbers 4 and 6. So basically, what we want is some kind of normalized coordinates between 0 and 1. We'll call that x1 and x2. And basically, we can calculate that using some interpolation equation. We don't need to worry too much about the details of this equation, but basically, what's happening here is we're adjusting the pixel values and the zoom values such that we have a normalized coordinate between 0 and 1. I've also added in here this n value, which basically for our use case just means 1. I've added it there for completeness because you may, in some cases, because you're dealing with floating point errors and whatnot, you may want a larger value in some conditions. But for us, let's just say n is there, it's 1, I put it there for completeness. Now, what happens when we receive a touch move event? What are the inputs at this moment in time? Well, obviously, we still have the viewport offset and the width. That hasn't changed. The user hasn't gone to a new tab or whatever. They're still touching stuff. And we know what are the new coordinates of our touches because we get that from the start event. The touch move event. And we could, if we wanted to, we could calculate the new normalized coordinates of these values using the same equation and just, simply inputting all the new values. But hang on a minute. What is this Z-min, Z-max with apostrophes? What are these things? We don't know these values. That's what we're looking for here, right? We're looking for a new Z-min and Z-max value such that the X values haven't changed, such that we're still touching the same numbers that we were touching before. So this is great. I know this does not look groundbreaking, but it is. Because think about it, right? This is not one equation. It's 2 equations, because we've got 2 fingers. And so now everyone, I'm sure you're all shaking because we know what's happening, right? We've got 2 equations and 2 unknowns. So what we can do is we can do a lot of very boring math, lots of stuff. This is my favorite slide in the entire deck, by the way. I had to scribble loads of notes on a piece of paper, and it took me ages to figure out how to put this on a Google slide. But I did the hard work. It's there. Look, we have an equation for Z-min, and we have one for Z-max. We can just use that. That's it. That's all we have to do. OK, let's try and code this up now. Let's start first with the touch start event. So what are we doing here? Well, as you can see, the important thing here is the toNormal function. That basically just implements the mathematical equation that I was talking about. And then our touch start handler, that basically, well, we have to keep track of the identifier of the touches, obviously, but we receive as inputs the CSS bounds and the two touches, which also contain the offsets of the touches. And here's what's interesting, right? Because if you remember, we specifically want the x-axis and the y-axis to be independent of one another. So what that means is all of this math that we've done also applies to the x-axis. Obviously, we have to use the height instead of the width, but we can just plug in all of these inputs into the math equation solver, and it will just do the same, do everything as we want for the y-axis. Now, what happens with a touch move event? What do we want to do here? Well, interestingly enough, we do something fairly similar. So we've got this one function here, solve two unknowns, which is solving these two equations. It's a little bit more convoluted. There's a bit more math going on in there, but we're doing the same thing. It's just giving us a z-min and a z-max. And here we do the same thing. Basically, we're tracking our numbers, so we find where they are by comparing the identifiers. And then we input all the pixel values that we have from our CSS bounds and our touches, and we input these normalized values that we calculated at the touch start event. And that's going to give us the new z-min and z-max, and we'll always be touching what we want. This is great, but now I've rambled for like 15 minutes and I haven't even said the word React, so you guys are thinking, what is this guy talking about? But this is not what we came here for. But it's okay. We'll take all this, we've done the hard part, let's try integrate this into React. So if we're gonna design a React component that's very robust and reusable, we want it to kind of work on any component, any subcomponent of a component, any subcomponent of a subcomponent. We want it to work basically on any HTML element. Okay, yeah, we can do that, because fortunately there is this feature called a CSS Transform, and that works on any HTML element. It has two components that we care about. It has a translation. We can use that for adjusting the panning, and it has a scale. We can use that to adjust the zooming. And obviously, those values come with the X and Y component to it. And so this CSS Transform, that's going to be our use state for our component. All right, good. Let's have a look at the component. So this is not a complete implementation. This is, if you want, like the skeleton of our component. What we've got here is our use state, which is just a CSS transform. And for this example, I've kept it simple, and I'm just using an image tag. But in practice, this works on any HTML element, but I've kept it simple for the time being. We put in our CSS transform and set the right origin, and that's the core of our component. Now let's integrate in our math solver. What do we need to do that? So this is the entire code of our component. What have we added here? Well, we've added a couple of refs. Obviously, we've added the container ref here. And because if you remember, our equation solver requires the offsets, the width, and the heights to do the math. So we got to keep track of that. And then I've also added an instance of our zoom pan solver. And so what's nice about that is we can call the useRef function, because really we don't actually care about the internal state of all the math that's happening. The only thing that really matters is if our CSS transformation changes, then okay, we need to redraw something. So that's the only state we need. And then I've also added some input handlers for touch start and touch move. But the handlers are actually nothing we're unfamiliar with. So we're just checking, have we got two numbers? Is the HTML element null? Don't do the default browser behavior, because browsers really love touch events. They really want to change stuff. So don't, just shut up for a sec. And then you get the bounds, because we need that for the math solver. And then you do the same thing on both the handlers. We're very familiar with that. So the only thing here that's missing is how do we calculate that CSS transformation? Let's zoom in on that. So this is how you would do it. So what I've done here, basically, I've added this toClient function, which is essentially just the inverse function of our interpolation function. Because think a bit about it, right? If you've got a normalized coordinate 0 and you input that into the inverse function, it tells you where that 0 is in screen pixel coordinates, which is what you want to translate the CSS. So that's good. We can do that to calculate the transformations for the X and Y axis. And then for the scale, it's pretty straightforward as well. So n is basically our 1. That's the maximum in the normalized coordinate space. You find the difference between the min and the max, and voila, that just gives you the scale. So let's try to have a look at it. just give me a moment to load up the demo on the iPad. Now I'll get a pop at any minute. Yes, there we go. Yes, accept that. Here we go. So this here is the component in full. So let's see that it does actually what it's supposed to. So we can zoom in here. That's nice. That's cool. OK. We can put 2 fingers on there and pan them around. That's good. Yes, that's panning. That's what we want. We can also adjust only one axis. For example, only adjust the x-axis by moving the fingers up and down. Yep, that's great. It does that. We can also do it left and right. OK, all right. It does distort the image in this case, but that's what we want, especially for the chart. And let's check that it actually is realistic touch gestures. So this is the tricky part of the demo. I have to make sure that I touch exactly where I want to. So let's try to touch the faces of these 2 sheep here. So if you put the faces on these 2 sheep, as I move this around, you can see that the 2 touches are basically always touching the same part of the image. Even if I distort it, it's still touching more or less the same place. So that's great. It's doing what we want it to do. There's a couple of caveats with this demo. So I'll go through them. So one of the caveats is that obviously a common use case is that you may want to say, for example, only adjust the x-axis. You'll put your 2 fingers like this close to one another and you'll move them apart. But here's the thing. So this may come to you as a bit of a shock, but I am actually not a machine. I'm a human. And so when I put down the fingers at the start, there was a little bit of wide difference between them. And it was very, very tiny. It was like maybe 1 or 2 pixels. So that means when I put the 2 fingers down like this, that causes the y-axis to be very sensitive. We can actually fix this, and that's what we do like on AG charts. If the user puts those 2 fingers like this, but the difference, the y difference is very, very small, we just ignore that. We pretend that it's 0, and that lets you basically just adjust the x-axis. Then there's a couple of other caveats. So let's say, for example, you put 2 fingers down and you move them around. Again, like I said, I'm a human. I'm not a robot. So obviously, when I move my fingers around, I'm not perfectly moving them in sync. They sort of go a little bit like, they move around a little bit. So you can kind of notice that the scale is a little bit like fidgety. It's like, make this big, make this small, big, small, and it looks weird, yeah. But we can fix that as well. So we can add some sort of like, snapping logic so that when you move it around, if the fingers are not moving by much, just ignore that movement. You could add some kind of logic for that. Then another feature you could do is what happens if the 2 fingers swap positioning. So let's say, for example, you go like this, whoa, like, yeah, OK. So in here, this is not very good. I've added a hack to basically say, don't ignore this case, OK? So when they flip around, my code is like, get hacky, and it's like, say, we'll pretend that didn't happen. But you could add that as another feature, right? So you could add some sort of mirroring effect to actually swap the image around if you wanted to. So that's, broadly speaking, how you implement a pinch to zoom component with independent axes in React. So here is a QR code to scan to check out the source code if you want to play around with the demo a little bit. It also includes the slides and some additional documents that explains how the math works. You can also try out the AG charts library if you want, because we've actually got an implementation of this. If you want to have a more realistic use case than just a bunch of sheep in England, you can try it out there. I definitely highly recommend. And I'll be available for any questions at this point in time.